In this video lecture, we're going to talk about the interaction between the compiler and the underlying operating system. So runtime support essentially covers all of these cases where we need to make sure that the program has the resources it needs when it's run. So after compilation, when you're running somebody's program, that they have all the resources that they need. So we want to manage these runtime resources for the program that we're compiling. There is a correspondence between the static structures where we are analyzing at compile time versus the dynamic or runtime structures, things that are going to take up memory during runtime, etc. So there's things like type checking we can do that's static, but then there's cases like recursive functions that we can't really predict how many resources it will take, right? The function could go into an infinite loop and take all the resources of a machine. So the compiler is somewhere in between. It needs to know for sure all of the static compile time information, but it also needs to lay out what is needed for the dynamic or runtime organization of all of the resources required. So it's mostly going to be about storage organization or memory, and how do we use memory to store the data structures of the executing program. So the execution of the program is under the control of the operating system. So when the program is invoked, the operating system allocates space for the program. All of the code has to be loaded into memory from wherever it is, like on disk. The operating system then knows the entry point, the so-called main function, and starts executing, gives control over to the program so that it can start executing in user space the program. So the memory organization looks like this. So the high address are all of so if you have the memory addresses, it starts from 0, goes all the way to FFFF, how many ever bits you have. So if you have a 64-bit machine, that's going to be 2 to the 64 is the maximum amount of memory you can address, which is quite a lot. So it's 18 exabytes or so of memory. This data space is where everything this memory is where everything has to fit. So the code all fits over here. So whenever you're executing some code, the operating system will put that into the memory somewhere and then start executing. It'll know a pointer into that memory and start executing the code from that memory space. The compiler is responsible for generating the code that will get loaded up there and then orchestrating the use of the data area. So we'll go into some details of what that implies. So when we are dealing with procedures or functions, we have two assumptions about functions and function calls, etc. in programming languages. One is that execution is sequential, that control moves from one point in a program to another in a well-defined order. So it's the sequence of instructions, you go from one to the other, right? And the second assumption is that when a procedure is called and it's finished, you finish the executing the procedure, the control will return to the point immediately after the point where you call that function or procedure. So these are the two assumptions we make when we are doing code generation and memory organization, but they're violated. So execution is not always sequential. You can have concurrent programs where control doesn't always move from one point to the program. So you could stop executing at one point of the program, move to a different point in the program, execute that for a while, or even do it in parallel. So different parts of the program could be executing in different threads, for example. But however, when we do code generation, we have to consider concurrency as a special case, right? So most of the time we just assume control is moving from one instruction to the next instruction. Control returning to the point after the call is also violated by things like exceptions. But again, these are usually cases where the program is terminating. So unwinding the stack and returning everything is done typically at the end of the program because it's an exception. So again, it's since it's exceptional, we can deal with it in that way. So when we look at procedure activation or activating a function, like calling a function. So when we invoke a function or procedure, we call it an activation of that procedure P. The lifetime of an activation of P is all the steps to execute that procedure, and then at the end we're going to return a value back, right? So that's called the lifetime. Something we want to track is what's happening in the lifetime of a single procedure. If you look at a variable that's defined inside this procedure, in the portion of execution in the lifetime of this procedure, X is defined during that time until X is deallocated. So lifetime of a procedure is a dynamic or runtime concept, whereas scoping, which is what we saw in the scoping lecture notes and symbol table, etc., that is a static concept. That's done when you analyze the structure of the program. You can analyze scope, but the lifetime is a dynamic concept. So we are going to track this lifetime, and it affects how the program is running and how many resources it's taking up. One useful thing is to look at activation in terms of trees. When a function P calls Q and then Q returns, before P returns, you're taking control into Q. Q finishes, goes back to P. P can execute some other instructions, and then P returns. So the lifetimes are properly nested. If P is calling Q, Q executes a bunch of instructions and then returns control back to P. You can see that this execution of Q is nested inside the execution of P. So the activation lifetimes of the sequence of calls can be depicted as a tree, an activation tree. So let's take an example. It's a very simple function, which is a recursive function. So this function Q calls a function P and then takes a value I out of that function and calls Q, which is itself, twice, one with m to I minus 1 and then I plus 1 to n. So if you look at this function and analyze its activation tree, you can see that when you start it, you give some value to m and n. So let's say m was 1 and n is 9. Call this function q19, which is going to call a function p with the same numbers, right? Same input m and 9. We get a value back, I, from calling P. So when P finishes, control comes back to Q, right? So it calls P, control comes back to Q. Q then calls, so let's say that P returns the number 4, then it calls Q with 1 to 3. Now Q is calling this function now with 1 and 3. And it calls P with 1 and 3, which then returns back a number. Let's say it returns the number 1. Then it's calling Q10, right? So after P is executed, the first thing that's executed is this invocation of Q. Let's say that n is, in this case, is not greater than m. So this conditional is not true, so it returns back to Q10, after which it goes to this Q invocation and calls 2,3, and that calls P and Q again. So these things don't recursively call Q again, so control returns back to Q here, and once it does that, it returns control back to this invocation. And now this is done. Notice that it has to, it's still not done with that function, right? The Q1,9 function is still, you've done this much, but it still needs to call this function Q here with 5,9. And that goes down and calls P, Q, and then 7,9, which generates these recursive calls. You can see that the lifetime of this function involves this kind of activation tree, and you can see it's dynamic because it depends on what these numbers are, right? So what the input is depends, what the size of the activation tree depends on your input, which is dynamic. So the activation tree depends on this runtime behavior, and it can be different for every program input since it's dynamic. And these activations are all properly nested. So we can actually use, instead of using a full-fledged tree, if we traverse that tree left to right, top down, we can actually use a much simpler structure, just a stack, to track all of the currently active procedures. So let's look at an example, the same example, but see how we can use a stack. So this is the same function that we had before, the recursive function. We start with, so I'm giving a simpler input here so that just to save space. So when I call Q with m equals 1 and n equals 3, I can store the currently executing function on a stack. So Q is still on the stack because it generates 3 different function calls. The first one is to P, and P has to come back and give a value for the variable I, the local variable I. So when P is done, we want to make sure that we remove it from the stack. We only want to keep track of the active procedure. So when P is done, we remove it, and we take the value of I and call the first instance of Q, which is here. And then after that, we'll call the second recursive call to Q. So when Q comes back, the first one, it gets removed off the stack, as you can see. And Q2, 3, which is the second instance, gets pushed onto the stack. It might generate calls to P, comes back, removes P from the stack. You get the first call to Q, which is done, it gets removed, and then it calls Q3. As you can see, it is going down 2, 3. So this is tracking the depth of the stack, is how deeply nested the recursion can go. And once we're done with it, we pop everything, and everything goes off the stack when it's done. Its lifetime is done. And finally, we're done with the function. It returns a value. If we look at the memory organization and look at where does this stack live in memory? Well, we know that we have the code over here. This is the instructions that will be executed, the program. We're going to start from the higher address just after the code part is done. We're going to start growing the stack all the way down from here, growing from high address to the low address. So every time we're going to know where the stack is by just having a pointer into memory that is called the stack pointer. And when we deduct a value from the stack pointer, we're allocating more space into the stack, right? So you subtract a value from this stack pointer and move it here, you're allocating more space on the stack for example, for that recursive function we just saw. So an activation record is what we need to save when one function is calling another. So if a procedure F calls G, then the G frame, the frame for G, contains the info about F and G, so that G can return control back to F when it's done. So F is considered to be suspended, and suspended in our case just means all of that information is kept in the stack, waiting there, and then when you pop the stack, you're back to F, and F resumes. So the frame in G contains information needed to complete the execution of G, all of its local variables, etc., and its parameters, and it needs information to resume execution of F. So what is a caller that called G? That information has to be there so it can give control back to F when it's done. If I look at a frame or an activation record, it contains a control link, a pointer to the caller, all of the local data, all the registers, because when it's suspending a function and starting a new function, you want to make sure that all of the register values get restored at the end of the function call. The return address and the link to global data, if any. So this is data that is not on the stack but is global. The parameters, these are stored on the stack as well, and the return value for the caller. So if you look at the memory structure, it looks like this. This is all the stack frame for function F with arguments A1 through AN. We're going to store the result of F on the stack. All of the arguments are here. All of the local variables and the temporary data are here. We have a frame pointer. So this frame pointer is used in order to tell us where is the information for f, for this function f. So for every function, we're going to have a frame pointer that tells us where is it that all of the information is starting from. And essentially that gives us a way, if I'm done with the function, I can reset my stack pointer up by adding a value to it, because you're going from low address to high address, remember? So when I reset the stack pointer to the frame pointer, essentially I'm done with the function and I get rid of everything related to the function. And this is it stores the caller frame pointer. So it stores a pointer back to the function that called it. So if f was, for example, the main function, it's going to have the caller would be the operating system that calls it, right? And every other function that main calls will have the caller frame pointer. This frame pointer would be stored for the main function that calls every other function in this program. So let's take an example of f calling another function g. So let's say that f calls g has some arguments a1 through am. The first thing we do is add some memory to the stack. So what we're going to do is decrement the stack pointer so we get some more space where we're going to store the result. This is going to be the result of g. And the reason we're storing it here is because it's going to be used. This is going to be used by function f, right? So that's why it's stored over there above the frame pointer for g. And now we have the arguments. The arguments are laid out. Again, these are arguments from to g. So again, we are decrementing the stack pointer. We have now added more space in the stack. Finally, we have all of the stack frame for g, which is very similar to the stack frame for f. Everything to do with the function called g, function called of g. And the stack pointer is way over here beneath the stack frame for g. G stores a caller frame pointer, which is this pointer over here. And since it's storing that over here, what we can now do is move the frame pointer down. This frame pointer now is a frame pointer for the function g. So now let's say that g is done. We store the result of g here. What we do is we're done with this function. So we can reset the frame pointer back to function f, and we pop everything off the stack related to the function g, and the stack pointer now points back to this point. Now if f calls another function, it's going to grow the stack from this point onwards, right? So it's reclaiming all that memory that g took up during its function invocation, during its runtime, and now it goes back to where it was before. It's back after calling g, and now resumes executing f. Now when f is done, it would move the frame pointer up and move this stack pointer up as well, and get rid of this information for f once f is done executing. So there's nothing really special about this organization. As you can see, the stack just means you have a pointer in memory and you're subtracting a value. That subtraction essentially is the allocation of memory to the stack. So you can rearrange the order of the frame elements if you want. You can divide it differently. Whatever is sort of consistent is fine. So the compiler can use any kind of consistent layout. And an organization is better if it improves execution speed or simplifies code generation. Essentially, that's what we care about in the compiler. And real compilers hold much of the frame as possible in registers so that it can create code that can be more efficient and use registers rather than main memory for the operations. A backend library like LLVM kind of takes care of this for you. So you don't have to do register allocation yourself. You can keep your, so LLVM uses alloc-a's, which is a way to store a location on the stack, but LLVM itself will try to map as much as possible from memory into these registers. So storing the registers makes it possible to reuse the registers between function calls, and that's the most efficient way for the code to execute. Particularly the method result and the arguments to the function, we want to store in registers as much as possible. We also have global variables, so these are not associated with any function. So all the references to the global variable have to point to some place in memory where the global variable exists. It cannot be part of an activation record. So globals are assigned a fixed address once for the whole program. And so these are called statically allocated memory locations. And depending on the language, there might be other statically allocated values. Depends on the programming language that you have. More or less things may be statically allocated. So when you have a memory organization that includes global variables, you might have all of your globals here stored just below the code, and then the stack grows below that static data. In some languages, you have a value that can outlive the procedure that creates it. So in this case, I have a pointer to this array, and I return that pointer. So when I return that pointer, I cannot keep it on the stack because this function foo is done. Everything related to this function needs to be popped off the stack. I can't keep it there anymore. So when foo's activation record is removed, bar still needs to be around because it's supposed to be returned back to its caller, right? What we're going to do in this case is use what's called a heap to store the dynamic data. So it's separate piece of memory from the stack. The stack has this nice growth, which is it grows and as the function finishes, it shrinks. So it has this natural growing and shrinking. The heap is more sort of haphazard, right? You can allocate various things. Different functions can allocate it. In some languages, you are responsible for deallocation. I am allocating some memory. I need to be responsible for deallocating it in languages like C and C++. Other languages have support for garbage collection for memory that's allocated on the heap. The code area contains object code. The static area contains the global data, global variables. The stack contains a frame for each currently active procedure, which is variable in size. It contains all of the local variables and local functions, etc. And a heap contains all the other data. So in C, heap is managed by malloc and free. These are the system calls that it uses to allocate and deallocate memory. And so both heap and stack can grow dynamically during the runtime of the program. So you must take some care to make sure that they are not sort of running into each other. So we need some kind of easy way to organize the memory. And the solution is to start the heap and stack at opposite ends of the memory and let them grow towards each other. So apart from the code and the global variables, the stack, as we saw, is always growing downstairs. So we subtract this pointer to allocate more memory to the stack. The heap is growing upwards from the low address to the high address. So the heap pointer here, you add to it to add more memory to the heap. And the stack is you subtract from it to add more memory to the stack. And if they meet in the middle, then there is a big explosion and you run out of memory. That's supposed to be a mushroom cloud. So in this case, the organization is fairly neat. Like stack is growing from high address to low, heap is increasing from low to high. And so you're not sort of using the same space. Everything is neatly divided in the memory layout. Now heap can have cases where you're allocating something in the heap and then you get rid of it. So it's available. So the heap can get fragmented. The stack, on the other hand, can't because it depends purely on activation of functions. So as functions stop, they go and release all of their stack memory and so on. We saw some cases where in some programming languages, the memory allocation even inside function scopes can involve the heap, like in a spaghetti stack, for example. But most of the time, it's fairly well-behaved. Stacks grow and shrink, whereas a heap is a little bit more chaotic. They can have these sort of fragmented parts of memory in the heap where different parts of the program are allocating and deallocating memory, and it can lead to fragmentation. So we have a stack pointer and a heap pointer, and this is how we manipulate the memory needed. One issue with code generation is alignment. This is a sort of annoying fact about modern CPU architectures. They use byte or word addressing to access memory. When they're accessing memory or laying out things in memory, they should be aligned in terms of 4 or 8 bytes. If you have a data structure or any kind of data for that matter, you have to make sure that the boundaries of the data line up with either a byte or a word, so 4 or 8 bytes. In a word, you want to make sure that the compiler is aware that this alignment can be an issue. So if the data is word aligned, it begins at a word boundary, right? So let's say you wanted to allocate this much, then you still have some extra space, and this part over here would be the word boundary. So you have to make sure that even if your data, you don't have sufficient data, you still need to allocate everything up to the word boundary. So most machines have these alignment restrictions, and there are severe performance penalties for poor alignment. So a compiler really has to pay attention to this. So here's an example where there's a string. It takes 6 characters, including the terminating null. Now, if I was to store this in memory, I need to make sure that there are 2 additional padding characters, that the entire string is fitting exactly at the word boundary, so that you don't end up with this penalty for being misaligned. So some compilers most compilers insert unused bytes called padding bytes. And this is not just for arrays or things like that, even structs or any kind of complex data structure. In this case, if there is space left over, because this structure doesn't have enough data to end up aligned at the word boundary. So on a word aligned machine, you have to, in this case, add 3 bytes of padding to this struct to make sure that it's word aligned. So in summary, we saw all the different cases of runtime support that we need for functions and how the compiler interacts with various system calls from the operating system. We have to deal with recursion, and we have to deal with all of the information that's inside each function. And so we store all of the information that we need for function execution in the activation record, and we push that onto a stack. And the stack memory is how we organize function calls, including recursive function calls. And stack allocation is really the easiest to implement while supporting recursion. Functional programming languages will often use heap allocation because of the way that they have scoping or how they do variable allocation. Sometimes they do lazy allocation of resources in functional programming languages, and that often involves using the heap. And in the video lecture for scoping in certain functional programming languages, we also saw that the symbol table organization also can't be a simple stack. It has to involve the heap as well.